Welcome to the session on applications. Our first paper is going to be DataliVR, transformation of data latency education through virtuality with ChatGPT-Powered environments. And the presenter is Hong Gao.
Okay. Thank you very much for the introduction. Hello, everyone. My name is Gao Hong from the Technical University of Munich. So I'm very glad to be here today to present our work, DataliVR, transformation of data literacy education through virtual reality with ChatGPT-powered enhancements. So in the digital world, we know data is everywhere around us, embedded in every aspect of our daily lives, and we are constantly generating and consuming data. Especially as researchers, we are working on data every day. So it's very important how we can manage the data correctly and efficiently. So this is where the data management comes into play. As we see, so data management involves a structured process across its life cycle, starting from data acquisition, cleansing, data analysis, visualization, and beyond. So effective data management requires the development of data literacy skills. So I asked ChatGPT to generate one brief definition of data literacy for me, and it says data literacy refers to the ability to read, interpret, understand, and communicate with the data efficiently. So data literacy skills is one of the most important 21st century skills, especially in STEM domains, where working with data is a daily requirement. However, the current data literacy education have a lot of limitations. For example, there are huge skill gaps exist among students, and also some students only have the limited access to the resources and technologies to support their learning. And most importantly, the one-size-fits-all teaching approach fails to meet the diverse needs from the individual learners. So to overcome these limitations, the future of data literacy education needs to focus on some key aspects, such as offering more availability, interactivity, accessibility, personalization, and experiential learning. So we know VR can offer a promising solution for the future transformation of data literacy education. So we know that VR holds a lot of advantages to support education. For example, VR can provide immersive and interactive learning experiences. Especially the advent of large language models like ChatGPT further transform the way of digital education supported by VR. So integrating large language models into VR can further improve education to provide students with more engaging, interactive, and personalized learning environments. So this work, we aim to explore how to support data literacy education through the integration of large language models with the virtual reality. And in this work, we developed a DataliVR, a VR application with the ChatGPT-powered enhancement for data literacy skill development. And we aim to provide students with an immersive and adaptive learning experience by immersing them in a series of gamified tasks regarding data management. So specifically, there are 4 key phases of data management learning, which includes data collection, data cleansing, data analysis, and data visualization. And we decided to use a basic fruit classification as a learning context, as this is a very daily activity, and then we can attract more interest from the learner. So more specifically, we use a decision tree classifier as a learning example. So in the first phase, the students will collect the fruit data, and also they will understand the data features, for example, why the fruit attributes are important for the further data analysis. And then in the second phase, they will learn how to clean the data and also how to prepare the data for the further analysis. through the gamified task. And based on the cleaned data, the students will next to analyze the data to perform the basic machine learning task, use the decision tree classifier. And in the last phase, the students will realize the data in a 3D format and interact with the data to gain more information from the data. So during the learning, there's a ChatGPT-Powered virtual avatar as an AI assistant, which means the student can talk to the avatar regarding the learning process or any questions related to the task. And to promote the learning, we implement a quiz session at the end of each learning phase. And also during the task, the student can receive the real-time feedback regarding their task performance. And to enable human-like dialogues, we implement ChatGPT-Powered avatar for real-time interaction. Specifically, we use the OpenAI's Whisper model for speech-to-text and Oculus Voice SDK for text-to-speech implementation. And in the two main learning phase here, we mentioned data cleansing and data analysis. So the students will experience two tasks. So first, they will experience the passive learning and then the active application. So specifically, they were first passively guided through the task where they learn important knowledge regarding data cleansing or data analysis, which is machine learning, basic machine learning concept. And then they will actively apply their learned knowledge to perform some exercise. So these are two main task sessions during each learning phase. And to evaluate the overall effectiveness of the introduced DataliVR, we conducted a user study with 30 university students as participants. And in addition, we also want to explore the potential effects of ChatGPT-powered functions on learning. So we applied a between subjects design. We have two conditions, without and with the ChatGPT-powered avatar, and we measured both the learning experience and also the learning performance. So after a brief introduction to the participant, they will sign a consent form and provide some basic demographics questionnaires. And then they will practice how to use VR and how to talk to the ChatGPT-powered avatar in VR environment. And then they will start the data literacy learning trip, which lasted about 23 minutes. And at the end, participants will fill out some user experience questionnaires. So our statistical analysis revealed some interesting findings. So overall, the participants rated the overall high user experience and high system usability of the DataliVR in both conditions. And particularly, the ChatGPT-powered function, here the ChatGPT-powered avatar, was found to significantly improve user experience and system usability. But interestingly, there was a notable deviation in the system usability item regarding the need for technical support. So participants reported less confidence when using DataliVR without the support of a technical person with chatbot condition compared to without chatbot condition. And then the participants reported their feedback on the absence and the presence of the ChatGPT-powered avatar. So participants rated the impact of the chatbot's absence on their learning experience as minimal. And this is mainly due to the well-structured learning task design, where participants received a smooth guided learning journey. But still, the participants recognized the significant potential benefits of having a chatbot to support learning with the DataliVR. And overall, the participants rated the high satisfaction with the presence of the avatar. And regarding the learning performance, actually we didn't find any significant effect of chatbot's presence on the task completion time. However, the chatbot was found to impact the participants' task performance. So surprisingly, the results reveals that participants achieved higher task accuracy in the without chatbot condition compared to the with chatbot condition. So a similar trend was observed in participants' performance in quiz session, though it is not significant. So actually, these results regarding the learning performance contradict our usual expectations that a ChatGPT-powered avatar would significantly enhance the learning outcomes. So overall, our results showed great effectiveness of the developed DataliVR in fostering data literacy learning from both learning experience and learning performance aspect. And we found different impact of ChatGPT. So especially ChatGPT did not lead to a better learning outcome in this learning context. So our findings offered valuable insight for the future research aiming to integrate ChatGPT-powered functions into educational VR applications. Rather than simply using ChatGPT for its capabilities and popularity, it is important to dive deeper into users' interaction with the ChatGPT-powered functions. And moreover, our findings highlight how the immersive nature of the task in VR can impact users' interaction with the chatbot. So users may become deeply immersed in tasks, potentially overlooking the role of the chatbot. So to address this limitation, the researchers in the future can implement some strategies to promote the interaction with the ChatGPT and find the balance between the high immersive learning task and the ChatGPT-based interactions. Yeah, I'm within 12 minutes.
Thank you very much.
Thank you very much. And questions? Yeah.
Do we have any questions?
Hi, I'm Irene from the Bauhaus University. Yes, I found it also interesting that you said that the chatbots seem to had worse results in the learning effects. Yeah. Do you have any hypotheses of why that was?
Yeah, actually, so the main purpose of this study is compare with ChatGPT without ChatGPT, right? So of course our expectations is ChatGPT can first of all increase the user experience, and second, definitely can improve the learning outcomes, right? But it's very interesting since the reviewers also complain about this, but we argue so it's important we all expect ChatGPT can improve learning, right? But in this context, we didn't find this significant improvement. So of course, the overall learning performance are all high in both conditions, but still, the ChatGPT didn't perform better than without ChatGPT, right? So as I mentioned in the discussion, the reason is because the whole learning, the DataliVR, provide participants with a very well-organized learning journey. So all the tasks are very immersed. They have even there's no avatar, but still they will get through from the beginning to the end. So this might be the reason so they didn't really can improve their learning, use the ChatGPT, but still they already immersed in the task and they can learn well. So that's our explanation of this result. Yeah. Thank you. Yeah.
Are there any other questions?
Thank you for the presentation. I'm Yanming Xiu from Duke University. So my question is, you mentioned that between the communication between human and GPT, you need to first do speech to text and then through OpenAI API and then text to speech. Mm-hmm. So I'm curious about what's the latency between this communication, and also is that satisfactory? Yeah.
I mean, there's a little latency, but it's accessible. I think just 1 second or something. But we tried different models, tried the best to solve this problem. But still, there's still 1 second latency. But I think in the real experiment, because we did 2 pilot study with the real the student, high school student, university student, but it seems nobody because we have questionnaires, nobody really complain about this 1 second latency. Yeah. So then we think this is not a problem in this application. Yeah.
Yeah, I think for 1 second it's totally acceptable. Yeah. Thank you.
Thank you. Thank you very much.
So our next paper is Immersive Study Analyzer, Collaborative Immersive Analysis of Recorded Social VR Studies, and Anton Lammert will be our speaker.
Right, just one moment, please. I think getting this out will make it a bit easier. All right, thanks for the introduction. As you can see here, this is work of me and my co-authors, Gareth, Rendle, Felix, Immohr, Annika, Neidhardt, Karlheinz, Brandenburg, Alexander Raake, and Bernd Froehlich from the Bauhaus University Weimar, TU Ilmenau, and University of Surrey. And I will just jump right into it. So in general, when we... this mode, sorry. Now, in general, when we conduct our social virtual reality studies, most of the time we record specific values, such as, for example, the velocities with which participants move their hands. In analysis, we then aggregate our data in order to inspect it. However, at this point in time, we might encounter some outliers in the data that we cannot very well explain. However, as we haven't recorded the social context within which these interactions happened, it is now hard to go back and actually identify the reason for those outliers. Immersive recordings can allow for a comprehensive capture of everything that happens in our virtual environment, meaning it records transformation data, audio data, state data, for example, scene graph information, as well as physiological data. We can see an example of such a recording here where a participant is actually trying to select boxes on the table. However, he does have some difficulties in doing so because the boxes don't behave the way he expects it. So in our example, maybe some of the outliers might actually be caused by a technical problem. Immersive recordings allow for in-depth analysis in virtual reality, meaning that analysts can investigate behavior from any point in our virtual scene in order to identify problems, in this case, for example, with the technical interaction. Our system is the Immersive Study Analyzer, or ISA system, with a specific focus on the collaborative analysis of social virtual reality studies, and introduces a set of functionalities for this, which I will present in the following. As mentioned before, our system allows the collaborative investigation of recorded social virtual reality studies. We can see a recording of such a study created by our system here, where two analysts are collaboratively investigating the recording. There is a certain behavior in this case that only analyst B identifies and observes. Through verbal communication, as well as temporal control, both analysts discuss whether they were able to observe the behavior. After identification that analyst A was in fact not able to observe it, both use temporal as well as spatial navigation to re-investigate the behavior collaboratively, as we can see here. This, however, is still not really sufficient for analysis, right? We do need some more functionalities. For this, our system supports the creation of behavioral codes or annotations within virtual reality, meaning that identified behavior can directly be annotated, and annotations are shared on a timeline between collaborators. They can be selected for temporal navigation and can be deleted as well. To enable asynchronous collaboration, they are also stored on a file server. Our system does not restrict analysts by always observing the playback at the current point in time jointly, meaning that analysts can actually navigate independently of each other in time. We can see this here, where the transparency is used to visualize the temporal distance between analysts. However, for joint discussion, obviously a temporal context can be re-established, as we can see here. To support the exploration of movement, our system enables the direct preview of trajectories within virtual reality, meaning that objects of interest as well as time periods of interest can be interactively specified, and after specification, trajectories are displayed within virtual reality directly. Also, they are shared between analysts in order to facilitate collaborative investigation. We can see that on each trajectory there are also spheres generated that, when hovered, display the point in time at which the object was located at this position. However, this is still not really enough, right? We don't really know a lot about all of these things because there is some context missing. For the investigation of more complex behavior, we facilitate query-based analysis, meaning that we can create analysis queries within virtual reality and see the results interactively. Here we can see an example where we create a query analyzing when the hand of participant Alice is close to her head. We can see that this happened quite frequently because, well, as we can see here in this example, participant Alice might have been adjusting her HMD. So, going back to our example, maybe some of the data, some of the outliers may actually be caused by just very uncomfortable HMD fitting. The context in which our system was developed has a specific focus on the investigation of audio. In general, our scene can contain a lot of different audio sources, such as the individual audio sources of remote participants, microphone audio from a local participant, as well as the audio that they've actually heard. Our system captures all of them locally for each participant at the same time and provides different modes for later investigation. In order to investigate the direct spatialization and transmission of the audio that participants heard, we provide the mode for playback of recorded output. This, however, can result in situations where actually the analysts are not able to correctly identify audio sources if their positions and rotations are not perfectly aligned with this of the participant. Because of this, we also provide a mode where individual audio sources that have been recorded are respatialized, enabling a more accurate identification of audio sources. Both modes can be contrasted in order to identify problems with transmission, spatialization, or audio mixing. As mentioned before, our system supports query-based analysis and has a set of base queries to do so. Audio queries, velocity queries, rotation queries, distance queries, and gaze queries. However, this has to be noted, it can easily be extended to other types of queries as well. The power, however, does not lie in the individual queries, but in the combination of queries for the analysis of more complex behavior. We might create a query analyzing when is user A talking, a query analyzing when is user A looking at user B, but we might also use logical operators in order to identify more complex behavior, such as when is user A talking and not looking at user B. We can see an example of such a query combination being done interactively in VR here, where we first analyze when is participant Alice talking, then analyzing when is participant Alice looking in the direction of participant Bob, and subsequently, after processing, creating a query analyzing when is participant Alice talking while looking at participant Bob. It has to be noted that all of this can also be done outside of VR using our system if necessary for analysis. As mentioned before, our system has a focus on collaborative analysis. For this, it shares annotations and query results between analysts as well as trajectory previews. It provides a voice chat, gestures, and rays for explicit as well as implicit communication. However, because of the support for loose and tight collaboration phases where analysts are actually able to navigate independently of time, we can have situations where analysts might observe completely different states of the virtual environment, as we can see here, visualized through the transparency. In this case, we know that collaboration always requires a shared context. We can use temporal navigation to re-establish this context. However, this can be inconvenient because it requires analysts to leave their current temporal position. Because of this, we propose a time portal, which can be used to re-establish this context through a stereoscopically perspectively correct view into the current state of the scene that another analyst is currently observing. We can see an example here where analyst B is actually indicating through the portal where participant Alice is currently located at in his point on time. So you can see it's already quite a complex system as of now. The ISA system is an open source Unity implemented system based on an open source C++ plugin that we've developed for recording, playback, and analysis. In addition to the standard data types, we also support generic data, which can be used for recording heart rate, latency, skin conductance, and eye tracking information, just to name a few examples. The plugin was designed to be usable independent of the engine and operating system employed, meaning you can also use the Unreal Engine or can use it on Android. And yes, it runs standalone. We actually tested it. We chose an expert evaluation to investigate our system, providing experts with two versions of our system, a base version with a focus on the annotation and behavioral coding, as well as cross-temporal collaboration, and an advanced version with a focus on the query and trajectory-based analysis. This evaluation was conducted with 8 experts from academia not involved in our development, from the domains of VR research and HCI. For analysis, we provided them with a real-world study recording created with our system. This whole process took 90 to 120 minutes and was later analyzed in a thematic way. Our findings show that all 8 experts considered our system to be useful, and 7 of them could actually envision that they would likely frequently use our system. The export of results was deemed as highly important, specifically for post-processing outside of VR. Experts identified several use cases, such as the in-depth behavior and conversation analysis, usability investigation, machine learning training data creation, and encoding for bias reduction, as well as training of other annotators. Towards the collaborative support, experts confirmed that our system successfully does this. During analysis, we observed loose and tight phases of collaboration between experts, marked here in the hatched areas. At these points in time, experts synchronized their playback in time to discuss certain behavior or discuss the task itself. The cost-tempered collaboration features also received a variety of feedback, only a few here. The audio playback was mentioned to interfere with collaboration, especially when analysts are located at different points in time. The time portal concept was found to be not easy to understand by one expert, and an adaptation was proposed that could actually show the point of view of the other analyst directly through the portal. In conclusion, our system supports collaborative analysis of social virtual reality studies, provides tools for coding and query-based analysis, supports tight and loose collaboration, is the first in all of those to do so, and was confirmed in terms of usability and utility by an expert evaluation. For future work, we plan to investigate nodes for asynchronous collaborative analysis, different functionalities in order to compare multiple study recordings, applications of queries to multiple recordings. This is already possible outside of VR, but not yet in VR. And we plan to support the community in using our tool, because we think it can be a research accelerator for researchers at these conferences or other conferences alike. Thank you for your attention.
Do we have any questions? I'll start with one. What sort of data? What format is the data that comes out of the system? So when someone wants to do some analysis on it.
So there are different types of data that our system, can produce. So in general, first of all, it is using a binary format in order to be efficient. So it's not shown here, but as we wanted it to run also on this Quest standalone, we had some performance optimizations such as multi-threading and ring buffering, and because of this we also wanted to have an efficient loading, meaning we used a binary format to do so. However, all of the data that was created can also be exported to CSV or WAV files afterwards. So we have utilities in hand that enable us to export all of the data that we've recorded, as well as our results, into just more general, typical forms in order to analyze it later on.
Okay, thank you.
Myung-Ori from Busan National University. So when you record the object in a virtual environment, do you select some specific object, or do you automatically choose all objects in the virtual environment?
Sorry, what do you mean with offset?
So this virtual environment, for example, have a table and then boxes and then 2 users, right? So when we apply your system into this virtual environment, the system detect all interactable object automatically, or do you need to select some specific object?
I see. Yes, so our system has different modes because we've used it in a variety of contexts, such as for recording VR lectures as well. And in some contexts, you might record everything, and others you might not. So to go back to your question, our system allows you to just check a box, and everything in your virtual scene is actually selected for recording. However, you always have the option to only select a specific subset that you're interested in. It also has to be mentioned that we have different modes for recording. In a study, for example, we were interested in recording all the position of all the objects at all the time, right? Because we want to have a very, very accurate playback. However, we also have a mode where we only record at, well, certain thresholds. So only if, let's say, the position of an object changes much more than 0.01 meters, for example, right? So we do have different functionalities at hand for that.
Yeah, so can I have one more question? Or okay. So I've tried that kind of approach, like when some object is moved a little bit, then we record the object. In that case, if there's a lot of object, it takes time to check every object positional differences, right? So how far your system can go?
So at the moment, and we've used it to record lectures with 35 students in virtual reality, averaging around 17,000 objects. So this is our system is capable of doing this at a rate of 30 steps per second. We can obviously always do more if we have more powerful hardware, but as of now, that's possible. On a Quest standalone, I think you should not run into any problems. There is a performance analysis in our system. So I think we show that 7,000 objects can be recorded at a rate of 120 FPS and also be played back on a standard normal PC. If you go to the Quest, it's a bit different, but still, we tried it.
Thank you very much. Can we thank the author? So our next presentation will be a remote presentation, and this will be an immersive and interactive VR dataset to elicit emotions. Weiwei Jiang will be giving this talk.
Hello everyone, thank you for coming to our presentation. My name is Weiwei Jiang. On behalf of my co-authors, I'm happy to present our work, an immersive and interactive VR dataset to elicit emotions. And this is our TVCG paper this year in ISMAR. And we are from very different institutions of the world, which makes us a very good team for this kind of emotion study. And we are very happy to present our work here. So first of all, let me introduce our motivation for our work. So what we are doing here is a dataset for eliciting emotions. And we all know that we have many different datasets already there for emotion elicitation purposes. Images, videos, 360 videos, especially for VR. And however, they are not very suitable for building your own VR applications. For example, these two 360 video datasets are quite famous that you can download and use quite easily. They are great. However, if you want to build your own applications, your VR applications, that it's very hard to integrate those videos into what your own application is for. For example, you build a VR game, and you want to enrich their emotional experience. And if you use this kind of data set, you can only play the videos and then continue playing the VR game, which is okay, but not very flexible when you come to the development. So what we do is we provide different VR scenes that you can easily modify and develop and do whatever you want for your own application purposes. And that'd be great for us, right? And it's open sourced, it's well tested, and it's ready to use. And which can be much better to use for this compared to those existing data sets. So, talking about the data set, the first thing we would like to think is what kind of data we're going to provide. And when it comes to VR emotional scenes, the first thing is scene selection. Is what kind of scene we should provide in our data set for emotion purposes. So what we think is about these things, effectiveness is, of course, first of all, the scenes should be effective to elicit targeted emotions, right? That's a basic requirement. That is complexity. We have more powerful VR headsets nowadays, but still we have limited resources that's not as powerful as a desktop PC. It's unfair to compare the computing service resources or the battery limitations there. So we don't want our scenes to be complex, too complex. Otherwise, we need a lot of the compatibility of devices will be not very high. And also, if it's too complex, it might be very hard to modify the scenes for your own purposes. And there are already many elements there. And what if you want to do something for your own purposes? Then that's not a very flexible way with the complex things, right? Generalizability is we want things to be generalizable in general samples or people. We know that emotion can be a subjective thing for different people with different experiences, different backgrounds. They may have different feelings about the same things. And we want our things to be as generalizable as possible. So even for different people, they can have the targeted same emotions as we designed. Diversity is for the different emotions, that we want our emotions to provide different emotions, not just happy or sad. We want to provide emotions as rich as possible, if we can. And potential applications is that similarly to the complexity things, we want our data set to be compatible with not only devices but also the application cases. So, for example, you want to build VR games or some other VR applications that you can ready to use our data set for enriching emotional experience, which will be great. So we have spent a lot of time on this kind of scene selection and modeling. So after that, we're happy to provide those 5 things for different emotions here. It's not a lot, like 50, but you can easily modify those things for different emotional purposes as for fine-tuning, as you can see. We also have a same thing for testing the things, which I will talk soon. So this is our protocol for testing the effectiveness of our data set. So our protocol is fully unsupervised. All the participants, they are required to have a MetaQuest 2 headset, and we developed an APK file, which includes all of our 5 things with other testing purposes, codes. And we also developed a cloud server for controlling the things and so also for collecting the data purposes. So specifically, the participants first, they will answer a pre-survey to sign up our study. If they have a MetaQuest 2 headset, if they are willing to run the study installing our application, for example, like that. And only after then, they will install our APK file into their own headset and run our study in their own environment. At the home or at office, it's up to them. We don't know where they are exactly, but they will do everything by themselves. And they will use the PIN code they have signed up by themselves to identify who they are. And they will experience all the 5 things by their own and answer how they feel about each thing after each thing. So we also collect other data, for example, the players' positions in real time for analysis purpose. And finally, they will answer a poster survey to describe how they felt about the study, for example. And after that, we'll flag the study as finished. And we will check our database to see if they have finished the study, and only if that, we will mark the participant has finished the study to ensure all the data collected are valid. And this is part of our results. As we can see, our participants are from different locations of the world. In total, we have 160 participants, 80 for each condition. 81 conditions for VR dataset, which is our dataset. Another condition is 360 videos, which is the existing dataset. We want to compare if our dataset is as valid, as effective as the existing ones. And we can also see the age distribution is quite wide, from 18 years old up to 62 years old. And they speak different primary languages, mainly about English, but also other languages. So in that case, we hope like our participants can represent the current VR users of the world. So this is the mean and distribution of the arousal variance of our data set for different things. And we can see that those emotions spread quite differently at different targeted emotions, from joy to sadness to some aroused, and other kind of emotional experiences. That sense, we can notice that we are missing the mean value for the high arousal and high valence quota here. That's part of because of the ethical restrictions that they might hurt themselves at these kind of cases. High arousal and high valence might be not quite safe for them to experience by their own. However, from the distributions on the right side, we can see there are still some people felt about high arousal and high valence at different scenes. This is quite interesting for emotional studies, like these things, because emotion is quite a subjective experience. Like people, for the same thing, they felt quite differently. Even though there is a mean value there are still like people have different feelings. We can see many people felt high arousal and high valence for all the things. And that might tell us something about how we build, how we modify the data set, or how we build the things if we targeted some kind of users for this different rich emotional experience. And for other experiment results, I'll give a quick pass. We have more details in our paper. For example, we can see like for all the things they all have different emotions for at least one dimension. Like there's different targeted emotions as we designed. And for the condition purpose, for the dataset and specific videos has no impact or has no significant differences there, which means that our dataset is as effective as specific video ones, the conventional ones, while we have more flexibility here for the development. And for example, we have these interaction recordings. Like we have recorded the player positions while they were experiencing in our environments. And you can see they were teleporting at different places to look around to see what the scene is look like. For the research purpose, we have restricted them to just one area, but actually our scene is much, much larger than this teleportable area. So which means there are more potentials for them to experience than this. And also the engagement time, most of people, they will spend a little bit more time there than the timer we set for them for different things, which means they would like to stay longer than they fix the time for specific videos, which is a good sign. We also have subjective measurements, for example, topic modeling, and we can find out, like even subjectively, people felt like these things were very successful in eliciting emotions. And interesting, we found that the shouting man with the gun thing, the high arousal one, has the emotional bleeding effect that will affect the emotional experience even after this thing has finished. That's a quite interesting finding. So in conclusion, we provide an open source, well-tested data set for everyone to use to build your own applications with emotional experience. And we have rich findings and guidelines in our paper to provide how to design emotion experience in VR. And those can be easily customized and fine-tuned. And data is already available now in GitHub. You can search VR data emotion. And you can also download here with this QR code. And it's already available now. So if you have any questions, I'm very happy to answer at any time. Thank you for your attention. That's the end of my talk.
Can we thank the author? Do we have any questions? I'll ask one to start with. Are you still having people collect, you still are having participants in the study?
Hello? Can you hear me?
Yes, we can hear you.
Yeah, cool. Thank you. Yes, we have this study run online, and the study has been stopped because we actually manually see if they have finished study and we pay them with the credits in the platform. So the study is paused, and we can resume it at any moment if we feel like we need to collect more data. That's the case of our participants recruitment. I hope that answered your question.
Yes, no, it did. Another quick question. Did you find any difference, because it was nice that you had different cultural backgrounds, did you find any difference, emotional responses based on the culture?
Thanks. Yeah, that's a really interesting question, especially for emotions. Actually, we haven't looked into that details for the differences yet. We have a lot of people from different locations, but we haven't started analysis in this part. But we can expect that from the subject analysis in the qualitative data, we do see that some differences there. For example, the puppy thing is kind of interesting. We can see actually there are two different, you can see there are two different peaks in the mean value set. One perspective that people feel like high arousal, high valence, low arousal, and some other people feel high arousal, high valence. Like they're really excited to see the puppy things. I think that's kind of impacted for some different cultural backgrounds there. And that similar things apply to other things. I think there are a lot of more interesting to be dig to if we look more into about the study results. Yeah, I think that could be an interesting visual as well.
Okay, thank you very much. One quick question. Sorry, I shouldn't be dominating.
Thank you very much for the talk, Kyoko from Japan. Really nice work. But I think it's a bit shame that we missed the data set in the joy part, the first quarter. Can you think some data set that is not ethically unacceptable, but still doable?
Yeah. Thank you for the question. Yes, we also feel like that's a little bit pity to miss that kind of order. But I think it's not very difficult to have for one of these kind of things. From our study, we can already see that even for the low arousal, low valence thing, some people feel like high there. One challenge here is like following the previous question is the emotion is very subjective. Like maybe like for example in Japan, people may feel like different. They will be excited from different things, and for different people, I think that's kind of subjective. And also for existing data sets, as we can see for the 360 views, there are not very many these kind of data points or videos that you can elicit mean high arousal and high valence emotions for different people. That's also one thing. But actually, in practice, I think you can easily do this by personalizing or customizing the experience for different targeted user groups. From our experience, we can see, that's quite doable.
Okay, if we can thank the author again, thank you very much. Okay, our last speaker today, the paper is Towards Energy Efficiency by Navigating the Trilemma of Energy, Latency, and Accuracy, and the presenter is Boan Tan.
All right, hi, welcome everyone. I'm Boyan from University of Illinois. This work is a joint effort with Ihan Pang, Mohammad Huzaifa, Shino Wang, and my advisor, Sarita Edvi. So in this talk, me and my collaborators will be discussing the challenges of energy efficiency in XR systems and how we can address them by making trade-offs among energy, accuracy, and latency. So today's mobile devices, such as XR headsets and smartphones, rely heavily on machine perception algorithms, which are critical for understanding and interacting with the physical world. While these algorithms require high accuracy and low latency, battery-powered mobile devices have a limited energy budget. Therefore, efficient energy use, or energy efficiency, is critical for enabling mobile systems, which is also discussed in the past few days, especially by the keynote speaker. Let's take two representative examples. Both Quest 3 and Vision Pro can only maintain a minimum of 2 to 3 hours of operating time, while the much newer Vision Pro even has a tethered battery with about double the capacity due to the increasingly intensive computation workloads. Using double the capacity for a roughly same amount of operating time shows a desperate need for energy and thus for energy efficiency. However, Algorithms are often optimized for accuracy and latency, but not for energy. While trade-offs can be made to prioritize one over the other, the absence of energy optimization results in two challenges. One is that a design makes trade-offs only between accuracy and latency can still be energy inefficient. And the other is that the trade-offs with energy as a new dimension are still unclear. We therefore aim to understand the trade-off space of energy, accuracy, and latency, and to design systems to minimize energy within accuracy and latency constraints. We study scene reconstruction as our target application because it is crucial in XR systems. And scene reconstruction reproduces the physical world in a virtual space that can be utilized by downstream applications and users. So the demo here shows that by fitting a video sequence along with camera poses, images can be integrated to build a consistent 3D model. The 3D model enables advanced features, such as 3D object detection and instance segmentation, where objects can be identified for editing or interaction. It also supports spatial audio for immersive acoustic experience by simulating sound reflections in the virtual space. While energy efficiency is a key for mobile XR devices, and there are a handful of energy-aware optimizations, we studied 3 of them and show that pursuing energy efficiency calls for actions at 3 levels. We first need to explore a broad trade-off space exposed by the optimizations, with up to 60x energy reduction, a 4x slowdown to 2x speed up in latency, and 0 to minor accuracy loss. We then need a co-optimization to achieve designs sitting on a Pareto optimal curve, which outperform others either in energy savings or latency reductions. We further need to identify the energy optimal design with targeted constraints from a cross-component analysis. Failure to do so can result in a suboptimal choice and up to 4x energy difference. Now, putting them all together, we show that scene reconstruction can be achieved at nearly 0 accuracy loss with 32x energy savings and 2x latency reduction. We will now dive into the details and begin with the energy-aware optimizations. Here we use green with sum up for better impact and red with sum down with worse impact, where darker colors and more sums meaning higher intensity. We first use the processor's frequency as a knob to treat minor latency for moderate energy savings. Here we show latency and energy as a function of frequency, both normalized to their maximum values. Within a certain range, a lower frequency saves more energy than the latency penalty incurred. And as shown in the figure, if we reduce the frequency from maximum to 80%, we can achieve 28% of energy savings at the cost of only 6% in latency. We then sample the input data to treat minor accuracy and latency for huge energy savings. We use a uniform sampling rate to control the trade-offs, which essentially represents the distance between 2 processed frames. And intuitively, a lower sampling rate favors energy savings but compromises accuracy and latency, and vice versa. We finally propose algorithmic changes by pruning computations and reconfiguring parallelizations to benefit energy and latency without hurting accuracy. The pruning effectively reduces 90% of processed voxels that contribute minimally to the final results. And for parallelization, we show a similar figure with energy and latency as a function of the number of threads. Rather than using all the threads, we use 4 based on the workload characteristics and achieves about half reduction in both energy and latency. While each of the 3 either brings limited benefits or compromise other metrics, we show that a synergistic co-optimization can harness the best of all 3. We want to emphasize that the key is not about pursuing the best for any particular optimization, but rather about understanding the trade-offs involved and leveraging co-optimizations effectively. A combination of optimizations and their tunable parameters leads to a design. In particular, we use 6 frequencies ranging from 100 to 50% of their maximum, and we use 6 data sampling rates ranging from 30 to 1 FPS. In addition to weather enabling algorithmic refinements, we have 72 design combinations in total. We implement and characterize these designs using the Open3D library. We use NVIDIA Jetson EGX Xavier as the hardware to represent the capabilities of mobile devices. We measure energy usage and frame latency on the Xavier board and use F-score for accuracy. We take the off-the-shelf Open3D running at 30 FPS as the baseline and run all the experiments on the ScanNet dataset. We show each design's energy savings on the x-axis and the latency reduction on the y-axis. Reductions are all normalized to baselines. So regions with darker green have better savings, while darker red means worse. And similarly for latency reductions. So with the baseline appears at the location 1 and 1, we know that optimal designs are expected in the top right corner. If we apply algorithmic changes, we can transfer the baseline to point A with both energy and latency savings. And starting from A, we use different colors for different frequencies, and similarly, we use the same color but different shapes for different sampling rates. We use marker size for accuracy loss, which is affected only by the sampling rate. So that is why the marker size is tightly coupled with the marker shape. The accuracy ranges from 0 to 1, so an accuracy drop of 0.01 can be negligible. Now, if we run a permutation, we can incrementally plot the designs for all the combinations, which are 72 in total. We make the first observation that the designs span a wide range in the trade-off space, exposing rich options for prioritizing one metric over the other. Designs can reduce energy up to 60x with latency impacts ranging from a 2x speed up to a 4x slowdown, while compromising accuracy by as much as 0.03. We then find a Pareto optimal curve, where designs on the curve outperform others either in energy savings or latency reductions. These designs are of particular interest, so we simplify the trade-off space by hiding others that fall below this curve. The full Pareto optimal curve can only be achieved by co-optimization. Here we show 3 segments of the curve that is achieved by applying only data sampling, only frequency control, and a combination. So applying each one individually can only access part of the Pareto optimal curve and thus missing potential trade-off opportunities. With the full Pareto optimal curve, identifying the optimal design is constrained by latency and accuracy, which are often application-specific. We show 3 latency constraints that corresponds to typical application rates of 30, 15, and 10 FPS, as well as the accuracy constraint for nearly 0 accuracy loss. We show 3 applications. Scanning requires high accuracy and low latency for timely feedback, which is constrained by 30 FPS and 0 accuracy loss, and results in the purple delta as the optimal design. On the other extreme, spatial audio can tolerate inaccuracies and delays, mainly because humans are less sensitive to acoustic differences caused by inaccurate sound reflections. This allows for greater compromises in exchange for huge energy savings, and thus results in the blue box as the target. And finally, a typical case like scene understanding allows minor accuracy loss, but still prefers low latency, which identifies the yellow hexagon as the optimal one. And as you can see, the optimal designs are all divergent from each other due to various latency and accuracy constraints. So pursuing energy efficiency without a clear understanding of constraints can lead to suboptimal choices, and thus leaving a 4x energy gap, as in this example. Precisely identifying the constraints requires cross-component analysis in a full system, which is often overlooked but needs more attention in the future. We further run sensitivity tests on 8 representative sequences using the design identified for typical scenarios, and we observe consistent results with an average energy reduction of 25x and a latency reduction of 1.5x, while maintaining less than 0.01 accuracy loss. Here we show a sample sequence again to show that the identified design can effectively mitigate energy usage while maintaining accuracy and latency constraints. We skip other results but refer people to check out the papers for more details due to time limits here. In conclusion, energy efficiency is a key for mobile XR devices, and we show that pursuing energy efficiency requires efforts that deserve more attention. We need to explore the broad trade-off space and leverage the designs that can achieve a huge broad space of energy, latency, and accuracy. We also need to co-optimize for optimal designs with optimizations enabling various trade-offs, such as frequency control, data sampling, and algorithm refinement, as we exemplified. We further need a cross-component full system analysis to identify target latency and accuracy constraints that are demanded by downstream data consumers. And again, we emphasize that the key is not about pursuing a particular optimization, but the concept and implications of the trade-offs, as well as the power of co-optimization. With all this in mind, I would like to conclude my presentation. Thanks for being here today, and I'm ready to take questions.
Do we have any questions?
Thanks for your talk. This is Xipeng from UNC Chapel Hill. A good talk, by the way. So I have two questions. The first one is, how are the implications and findings applied to other applications, like exemplifying another workload?
Right. So while we use scene reconstruction as a representative application, the implications and the concepts we introduce in this talk are actually generalizable. So if you're asking for a different workload example, I can say, for instance, if we're talking about a deep learning network for machine perception, so while we use particular algorithm refinement for scene reconstruction, for TSDF-based scene reconstruction, similar pruning philosophies can also be found in different neural network-based methods. For instance, knowledge distillation or network pruning. And then for the data sampling, this is input data dependent. So if we're talking about the video stream as input, then this also applies to another workload, like the DNA object detection. And again, for the processor frequency control, this is actually orthogonal to the algorithm. So, but you can always propose new and better trade-offs, and that's actually what we encourage people to think about.
Cool. I also have a question on how these implications could be adopted by researchers in this community, like any actionable methods?
Right, right. So we understand of taking energy into consideration for researchers with different focuses can be challenging and difficult. So we believe this requires a higher level of collaboration and interaction for people from different domains. And to take the first crack, our group actually, we have built a fully open source reference system, which is called Elixir, and this allows you to customize your own component, your own application modules, and also have access to low-level data sources like camera images and IMUs. So we welcome people to check out the details, and please feel free to reach out.
Cool, thank you.
Hi, Edward from Carnegie Mellon. Great talk, by the way. I just have a quick question about when you say you're scaling the processor frequency, is that just for CPU or also for GPU?
So in this application, we tested it on CPU, but the frequency scaling characteristics is fundamental to CMOS logic. So that also happens on GPU.
But are there different, is there like a, oh, okay, that's good.
If we can thank all of our authors, thank you very much.